Okay, so welcome everyone again to the course. I'm going to now cover the flow equation today. And that's the second part of the course after knowing about porous media, porosity, permeability, the way we measure them in the lab, the way we can model them with bundle of tube theory, and then Kalman-Kozeni's empirical corrections and the concept of tortuosity and others. Now we are trying to say, okay, we know Darcy's law, we know porosity, we know permeability. Now let's describe flow. Let's describe the dynamics of flow through porous media. So that's the subject of today's lecture. How would flow behave or happen? How can I find potential? How can I find velocity across sections of my porous material? That's the subject of today's course. Now, the learning objectives are these two bullets. The first is we are going to review or revisit the incompressible flow formulations, describing how incompressible flow through porous media happens. When I say flow equations, you're going to see that I say many times flow equation or I say pressure equation. They are interchangeably used. When I say flow equation, I mean pressure and velocity. So these are the flow. Transport means the species transport. So we have flow equation, we have transport equation. Flow is pressure and velocity. And then we are going to solve that 1D problem for 1D Sandpack problem analytically. And you need this knowledge for doing your first project. Your first project has a chapter on analytical solution of this process. So this is something you need for your first project too. Okay. There are different classifications that we need to set before we start with the course. One is that the flow happens in different compressibility ranges from fully compressible, like gas flow, gas reservoirs, hydrogen reservoirs, gas reservoirs, and so on, all the way to the incompressible. And it's not that we have fully compressible or fully incompressible. There is a slightly compressible range as well. I've covered it already in simulation course. So we can be fully incompressible, we can be slightly compressible, and fully compressible. Slightly compressible flows are addressed in, let's say, oil and gas, high pressure gas, or poromechanics concepts. A lot of poromechanics problems are described with a slightly compressibility. A lot of subjects of next quarter simulation course will be about compressibility concept as well. Here in this course, we are going to focus on incompressible flows, which means density of the fluid does not change when it passes through the porous medium. Density is constant. Porosity also does not change due to the pressure of the system. So it stays constant over time. In terms of time dependency, we can have a steady state systems, which means change over time is zero. They don't change over time. All the way to transients. In between, we have another system, which is pseudo-steady state or pseudo-transient. Again, these are the subjects which are very relevant for well testing and stuff. I'm not sure if I would cover it this year. What we are going to focus is in this course, in this lecture, is steady state incompressible flow. But we are, as engineers, aware that the physics in the nature spans broader ranges. Good. So let's do that business then. I would like to ask Pelle to tell me, when I look into the nature, man, we are gonna have some sort of interactions today.
I'm looking forward to
it. So I'd like to ask you, my friend, let me first set the environment very constructively. So I'm looking in the nature, and I'd like to describe it with engineering tools, with mathematics, so that I can design processes, I can optimize, I can do stuff, I can understand and analyze it. What are the principal basis for me to help me translate the nature into mathematics? What fundamental equations would I use in order to translate what I observe in the nature to mathematical formula?
I think location and time are the most fundamental things. So maybe
location and time are information sets for describing properties or the location coordinate or locate species. I would like to see how the system behave. How does the system behave, or how the system behaves? And I would like to know over time and the space, the parameters you mentioned, how would the properties like pressure, velocity, temperature change? What fundamental equations would allow me find out how would the temperature, pressure, velocity change over time in different locations? What are those equations?
differential equations.
Which are based on what concept? These
Derivatives.
differential equations have derivatives with them, but they are developed based on some laws. What are those laws that allow us
conservation laws?
Absolutely right. So we have conservation laws that say mass, momentum, energy are conserved in the nature. So in the location and time, as Pella said, we'd like to describe our system properties over time, dynamically. The pressure, temperature, velocity of the system change over time, but they don't just change randomly. They follow some physical principles. And the principles behind these changes are based on conservation laws. So conservation laws would allow us describe the dynamics of the system and its properties changes over time in different location in the space. So in that case, I start from nature. When I want to describe PDEs, partial differential equations, to describe the system properties, there is a major help that I will receive from to translate nature into mathematics and engineering. I use conservation laws. Those would help me translate the nature into math. So you will be, working as engineers in many different disciplines. I mean sectors as well. Sometimes many of you may want to just optimize something. Imagine this falls. It doesn't have to be flow in porous media. I mean if you want to model this, again, you need to go through conservation laws. And obviously, conservation of momentum is another conservation, which is forces. External forces is equal to, all of them would be equal to ma. Acceleration would be coming from that principle of second law of Newton. And there are, of course, other things here that would help, but conservation laws are allowing us describe PDEs to find out the dynamics and changes that happen in our system. Now, this means that I'd like to describe at the continuum scale the dynamics of my system. Conservation laws would be mass conservation. Instead of momentum conservation, we use Darcy's law. Darcy's law relates velocity and potential gradient. For us, is replacement of momentum conservation. If we wanted to do porous scale modeling, we might have needed Stokes equation or Navier-Stokes. We are at the Darcy's scale. At the continuum Darcy's scale, we use Darcy's law. Of course, they are not enough. We need to know how the pressure volumetric descriptive of the system and temperature are related. PV is nRT, PV is ZRT, or how the phases are formed. What is the state of the system? Is it in liquid, vapor? Are they mixed? How would this happen? Equation of a state would help us describe the phase and physical properties with the given thermodynamic conditions. At the given pressure, temperature, or enthalpy, or mass concentration, we could describe the distribution of the phases of the component. And obviously, everything we do, every system in engineering would require boundary conditions. And depending on if it is a steady state or it is having time dependency in it, it needs initial condition too. And we should also remember that we are at ReV scale where we can describe density, viscosity, properties like that. This is something we have already discussed in our lecture 1. So if you are missing them, just go and watch those videos. Now let's start. We are going to describe change of pressure and velocity over time. Well, if we are speaking about is steady state flow in this class, so it's not time would not, if time passes by, nothing would change. And over space. So at different locations, we would like to know what's the potential, what's the pressure, and what's the velocity. Let's gain some knowledge about this. And then, after we gain the knowledge, we start to solve a practical problem. Is everything so far clear to everybody? Do I have everybody on board still? Yeah? Good. So, oh, I'm sorry, I just pressed the wrong button. I may accidentally mute you. It's just unintentional because I need to just click some places on my screen to go back to the lecture. Okay, let's do so. The most fundamental way to describe conservation of any quantity which is conserved would be described this way. I have a control volume, which is a fixed volume in my stream of flow. Which means that I have flow of fluid happening like this. Arrows show the flux. I have drawn a fixed frozen control volume. And I would like to understand mathematically if the quantity psi is conserved, or let's call it x. If this x is conserved, how can I describe that conservation of the intensive property x, which is conserved? Conservation law says if x is conserved in your control volume, this domain here, change over time of the entire amount of x in your control volume, omega. So this control volume is called omega. The sum or summation, or if you are in continuum space, integral of all amount of x in your domain, the sum of all x would change over time if you have net outgoing flux of x, or you have source terms or sink terms. The second term here is the integral, which is summation over boundary of omega. This is boundary of omega. of the flux of x, so x is traveling with velocity u, and then you are gonna integrate it over the entire area. So this is the area that I'm now drawing. So omega is inside. This is boundary of omega. So this says x is traveling with velocity u, and so it's its flux. If you integrate it over the entire surface with positive to be the normal direction and outside of the domain, negative inside. So therefore, outflux is positive, influx is negative. Then this integral would be net outgoing flux of x, because the vector n is positive, is defined to be positive if it is pointing outward. If the flux is outward, it's going to be positive flux. And then sum all the sources that you might have for x. Now imagine there is no source term for x. There is no consumption. If you put it in the left-hand side, it will be consumption rate of x. If you put this integral to the right-hand side and assume that injection is positive, then it would be injection would go to the right-hand side. This is consumption. So if there is no source term q, if the net outgoing flux is 0, it means outflux minus influx is 0, which means whatever leaves is exactly the same as whatever comes. Then the difference between the two is 0. It means then this becomes 0. This second term becomes 0. If this second term is 0, which means whatever leaves is equal to whatever comes, there is no source or sink term, then what can we say about change over time of x? Would x change over time? Rene, what do you think?
I'm going to assume here that you noticed I was drifting off and didn't really pay attention on that last slide. And I have no idea what the question is.
I'm sorry, what is it?
I have no idea what the question is.
The question is, if I do not have any source term, okay, and I do not, and net outgoing flux is equal to 0, what would be the change of the amount of x over the entire control volume?
It would go to 0.
Yes. Why? Because conservation law says so. The amount of x would change if you are adding some mass to the system or quantity x, or you are having a flux of it out or in would imbalance. So you have more out than in, or you have more in than out. That would cause change of x. If the second term is 0 and the third term is 0, no production consumption rate, no net outgoing flux, then the amount of x would not change over time. Now let's do this generic conservation law for everything. What are the conservation laws that we need? We need mass conservation. Instead of momentum conservation, I want Darcy's law. And do I need heat or energy conservation law? No, I don't. Why? I'm assuming isothermal process. So I'm just assuming that the temperature is constant and I don't have to worry about energy conservation now. So I'm going to only describe the system which would have only the mass. We are speaking about single phase flow in porous media now. But before we do the real equations right up, I'd like to just say that was the governing equation. That was the conservation of x, an intensive quantity, change of it over time, plus net outflux of it, plus the entire source term would be 0. Now let's do a little bit of mathematics to obtain the PDE that Pele said at the beginning, that we need PDEs to solve, and not in this integral form. So what do we do is that we work with the second term here and use divergence theorem. When you apply divergence theorem, then you get the integral over volume of the divergence of the fluxes that I have integrated over the entire volume. So this divergence theorem translates the dA, the area integration over the surface, to the divergence of the flux integration over the volume. Now, this is integration over volume. This is integration over volume, and this is integration over volume. I can just combine all of them if I want, right? So I can just cluster all of them and form what I would like to form. So this would become integral of what? This would be integral of, now I need to have the entire integral with me, but my PowerPoint font is somehow doesn't work on my tablet. So what I am going to mainly do now here is that I'm going to just say, let's see this. I need to collect all the integrals into one integral. So I'm going to say it's integral of omega for d dt of x plus divergence of xu plus q dv equals 0. This way, I have collected all these integral. I have factorized it and put it all in here, and then I have all of these in one part. If integral of something is 0, if integral of something is 0 for any dv, for any volume, if the integral is 0 for any volume, then naturally you are going to have one property here. And the property is that this term here must be 0. If integral of f over any dv is 0, any volume is 0, the term itself needs to be 0. So that would be dx dt plus divergence xu plus q would be 0. The term inside the integral should be 0. Now, this is the partial differential equation we like to have. This is PDE. We worked from this integral conservation law. We worked it out and found what is the corresponding PDE for that integral equation. Okay. And now we are going to be interested to stay with this PDE instead of this term. We will work through the entire course with this formula. If Q is in the left-hand side, this is production or consumption rate. This is production. If it is production, it is positive. If I write Q in the other side of the equal term, it would be injection rate, would be positive. Now let's go forward and find out how can we describe mass conservation in PDE. Okay, so let's do mass. So I'm going to skip this slide because this is, again, if I want to fill it up, it will be integral over omega dx dt plus divergence xu plus q dv is equal 0. That makes it to become dx plus divergence xu plus q equals 0. That's exactly what I wrote here. They are the same. And that's the general PDE, general differential equation describing any conserved quantity x. It can be used for mass, it can be used for momentum, it can be used for energy. Now let's go forward and find out what is the mass conservation with this PDE form. Okay, so how would I go forward with this? If I want to do mass conservation, my conserved quantity, which is x, becomes density. Density is the intensive parameter corresponding to mass conservation. So I'm going to replace x with density rho, and that would give me my mass conservation. It used to be ddx of t plus divergence of xu plus q is 0. That was my generic PDE for conservation law. Okay. Now, if I use density for mass, what would I do? So instead of x, I'm going to do mass here. So I'm going to replace x with rho, which is density. Then instead of x here, I'm writing rho. Instead of x times u, I write rho times u. And I assume there is no source term or sink term, so q is 0. Then I find that to be my mass conservation. And sometimes it's also called continuity equation as well. Okay. Now, if I assume the system is incompressible, what would it mean? What would incompressibility mean?
The volume stays the same.
Absolutely. Which means in terms, I have density and I have velocity. Which term stays constant if system is incompressible? Density. Fantastic. Fantastic. So if it is incompressible, it means density stays CTE constant. It would not change over time. Which means I can cancel, and obviously its derivative with respect to time would be also 0. When density is constant, then its derivative would be 0. And also divergence of rho u can be written as rho divergence u, because rho is constant. It can come out of the ddx, ddy, ddz, because it's constant. It's a factor, like 2, 5, 1,000. So with these, if I look into my most generic conservation for mass without source term, with the assumption of incompressibility, what would I get? The first term would be 0. I need someone who has not spoken so far to speak up. Anyone who hasn't spoken so far? Unfortunately, it's hard for me to manage my screen and locate you. Or Freak, are you with us?
Yes, I'm here.
Okay, great. So Freak, if I apply these considerations of incompressibility, what would this equation end up with? What should I do with d rho dt? Would it be 0 or not?
I really don't know, I'm sorry.
Okay, no problem. So we just said that when your system is incompressible, your density is constant. And therefore its derivative with respect to time will be 0. Okay, so that means that if I have incompressibility in the system, d rho dt plus divergence rho u was my real governing equation equals 0. This term will be 0 because it's incompressible. With rho, I can bring this density outside the divergence operator because density is constant. So this becomes rho divergence u is 0. And since rho is constant, I can get rid of it too. So it will finally reach me to this point. Divergence velocity is 0 if there is no source term. If there is no source term, my mass conservation becomes divergence velocity is 0. What would it really mean?
Sorry, I missed. Why do you cancel the second
Density, because it's constant. Because it is constant. Who is speaking?
This is Ren speaking.
René.
Yeah, I get why you ignore, of why you can cancel the density derivative, but why can you cancel the second density too?
That's a great question, because rho times divergence u is 0. Okay, since rho times this divergence velocity is 0 and rho is constant, I just divide the term with density. I just get it out.
Yeah.
That's why. Okay.
Yeah.
Thanks
okay,
a lot,
yeah.
of course, but that wasn't clear from what I explained. Thanks a lot for bringing this. So this is constant, so it doesn't have to stay in the system. I can divide it by density and get rid of it. Which means at the end of the day, I reach to divergence u is 0. And that's very important for us. Now, this is something that we need in order to now to go forward and do more study with this conservation law. Divergence u is 0. I'm going to explain this many more times. Means that whatever goes or leaves my control volume is the same as whatever comes. Divergence mathematically reads divergence. Physically, it means net outgoing. Net outgoing. When divergence of a flux is 0, it means whatever goes is equal to whatever comes. And that's precisely what incompressibility means in the absence of source term. If there is no source term, whatever leaves is equal to whatever comes. Because there is no other way to change mass of a fixed volume. Because if you wanted to increase mass of a fixed volume, you had to allow for compressibility. You had to allow squeezing of molecules and allow more mass to accumulate in a fixed volume. And that's not possible. And the good thing about this lecture is that it's going to be recorded and you'll be able to watch it many more times to get these concepts fully developed with you. And this is something that you will also observe in nature as well. When the system is incompressible, there is no change of density. So you cannot fit more mass in a given volume, fixed volume or control volume. Then if there is no source term to it, whatever comes should leave. If whatever comes doesn't live, you need to increase the mass, but you can't because the system is incompressible. Now with this, I would like to move forward and say that is my mass conservation. Darcy's law has been already well explained before. U, or velocity, is minus K, absolute permeability, divided by viscosity of the fluid times the potential gradient. Now, look at this. You have a velocity here. And Darcy's law relates velocity with your potential gradient. Or if you don't have gravity, with your pressure gradient. Remember, phi was what? Can someone who has not spoken please speak up? What was phi?
Potential.
Exactly, and that is?
The difference.
Pressure plus
Rho G Z
rho g
or
z.
height.
Absolutely right. Thank you very much. Now, if I combine these two equations, what would I get? I get divergence of velocity is 0. Divergence of velocity is 0. Now, I want to use Darcy. Oops. I want to use, I lost all my notes again. So I start with divergence of velocity is 0. So that means that I can now use my velocity here with Darcy's law and then write it as divergence of, instead of u, I can write minus k over viscosity, gradient potential is 0. This
I had a question. Oh, I had a question on the first one. Because you say that what comes in equals what goes out.
yes,
But the U is about velocity. So what does it say about velocity?
it's actually about velocity, which means whatever you have is coming with the speed, with the velocity, right? It comes because it has
true.
velocity. So velocity is the flux, is the volumetric flux. If you multiply by density, it will be mass flux. But U is precisely, imagine you have this control volume. Whatever comes is equal to whatever leaves if there is no source there. Okay? And we have got rid of density rho because it was constant. Otherwise, it was actually divergence of rho u was 0. So the rho would make it mass. But since it was constant, we brought it outside and then actually we just got rid of it because it was constant, we just canceled it out as if you divide it by the rho. 0 divided by rho becomes 0. Rho u divided by rho becomes u.
But if rho wasn't constant, you would also have the d rho dt term.
That's precisely true. And that's exactly the difference between compressible systems and incompressible systems. With compressible systems, you not only have divergence rho u, but also you would have ddt of rho involved, which means rho can change over time as well, because it's compressible. It can change. You can squeeze your gas or you can decompress it. Precisely. And we are going to repeat these concepts through the entire course because this is exactly one of the pillars of flow in porous media concept. What I have reached so far is this equation. We call it potential equation. Or many times we call it pressure equation. If we, instead of potential, we write it as divergence minus K over viscosity, gradient of pressure plus rho g grad z, which means we only use rho g in the vertical direction in where the gravity is acting. If not acting, we don't really use it. You can also sometimes write it this way. This is pressure equation. In this course, I actually like very much if we work with potential because it's simpler, it's more convenient. Once we obtain potential, we can calculate pressure with it. We can calculate pressure from potential by saying that pressure plus rho gz is potential. And if I just give you a sample, horizontal sample, then gravity is not acting, pressure and potential would be very easily just correlated because elevation z does not change. So then they would just be offset by a constant factor. Anyhow, I have written it already in here a bit neatly here. Continuity equation gives us divergence u0. Darcy's law gives us relationship between u and potential gradients. If we combine the two, divergence u can be written as divergence minus k over viscosity, grad potential is 0. Again, in the absence of source term. What are the assumptions we have made so far to reach to this point?
the density doesn't change. For example.
Density, so incompressible flow. Incompressibility is a main assumption we have done. What else have we assumed?
I think that we have a vertical porous media, that it's not tilted.
No, we could have it in any direction. That's a generic term. Divergence can be ddx, ddy, ddz. It can have all the dimensions that you would like to have. So you could have any, okay? Because we placed it at gradient operator. If I would have written it as ddx or ddy, yes. But at this moment, I just said gradient, which means any direction can be there.
We also assume.
Yeah.
We also assume there's no mass source term.
That's a great comment as well. I have no source term here. If I had source term, I should have written it as equals to Q or some source terms. That's true, absolutely. What else? Do I have heat? Do I have temperature change?
No.
No, it's isothermal, so heat doesn't change. I mean, we don't have heat conservation here written because we assume that heat doesn't change. I mean, it's an isothermal process. What else? All the assumptions that I have made to obtain Darcy's law are still in place here, right? Laminar flow, Reynolds less than 10, no slip condition, all those assumptions that we discussed last time about Forchheimer. There is no Forchheimer here, right? It's Darcy's law. There is no Klinkenberg effect here, right? It's Darcy's law. So divergence U is 0 is only valid when you have incompressible flow, irrespective of Darcy or non-Darcy. When you combine it with Darcy's law, you will add all the assumptions that Darcy's law has in order to just reach this pressure equation. Divergence U holds irrespective of porous or non-porous media, irrespective of Darcy or Forchheimer or whatever. Always, due to continuity, due to mass conservation, divergence U should be 0. Then, specifically for porous media at Darcy's scale, we relate velocity with gradient of potential this way, and so we get the pressure equation this way, or potential equation this way. So that potential equation is now subject to all the assumptions that Darcy's law is subject to, or yeah, okay? But divergence U is 0 is valid if you have incompressible flow with no source term. So this is valid if you have incompressible flow and no source term. If you have source term, you write it divergence U is Q. If you have source term, you write it divergence U is Q. And that Q can be injection Q when it is positive. So with source term. This is with source term. If you have compressibility, then you need to add ddt of density and rho U, divergence rho U. Now I'm going to speak about how are we going to solve this problem. We first solve the potential equation to find the potential. Once we know the potential distribution, we can find the velocity distribution later. So first we do flow equation solution. Then we solve velocity. Once we know potential, by the way, we can always calculate pressure too. And that is our system. This will be solved. From that, we are gonna find other unknowns, okay? And we have different types of boundary conditions. In general, we have Neumann, which is flux given, or Dirichlet, which is the value potential is given. And these are the things that I cannot just teach and lecture about. We just need to do this in practice. And your project 1 is about those. Solve potential equation analytically, then solve it numerically, and then go to the laboratory, measure the potential, everything experimentally, and find out how the potential and velocity and pressure distribution look like in porous media. So all these collective, constructively aligned activities are to, at the end of the day, at the end of this quarter, to let you feel comfortable and confident about incompressibility, compressibility, source term, no source term, potential, pressure, gravity, and all these terms. Okay? So I am going to just go through quickly to some of the mathematics for 2-3 minutes and give you a break, and then we will continue. This is just a review of math, but at the end of the day, what you should cover is just simply the final equation, but it's important to be complete here. I just wanted to make just a note here for those who come from different disciplines that divergence of u or divergence of anything means derivative with respect to x of the x component of that vector, derivative with respect to y of the y component, velocity y, derivative with respect to z of uz. So divergence of k over mu grad phi at the end can be expanded based on ddx, ddy, ddz this way. And here I'm assuming that kx, y, and z are the same. But these are the things about heterogeneity and anisotropicity that I'm going to teach next week. And there we are going to see that k not only can be kx, kxy is there, so we have even not only anisotropicity, we have also some other effect of full tensorial k. Here, just assume the simplest possible k for now, absolute permeability. We are going to see next week, and especially our geology students know a lot about it as well, that k can be very, very complex, and this is the subject of next week. So if I write it for 1D problems, then I have one direction of change, either x, either y, either z, whatever I like. Let's just take it x, but you can replace it with z if you want, or with whatever else you would like to. So I have ddx of ux in 1D, which means ddx of k over mu d phi dx is 0. That's 1D equation. If my k is homogeneous, so if k is constant and viscosity is also constant, I can simply cancel these two terms if they are constant. So for homogeneous systems, I reach to the most or the simplest form of the pressure or potential equation. When k and mu are constant, my potential second derivative over the space would be 0. If I write it based on z, it would be d second of phi with respect to z, 0. Now, if I integrate that, what function is it? What function has the second derivative 0? What's the function that has its first derivative 0? If phi is constant, absolutely. Constant number has its first derivative 0. What function has its second derivative 0? It should be a linear, absolutely. It should be a line. So phi here would be a x plus b. Any line would have its second derivative 0. First derivative of a line is constant a, second derivative would be 0. If I would have described it in z direction, it would be a linear function of z. That would be also no difference. That would be 0 as well. So let's do that. Let's go to this experiment, and that's the rest of the course today. And I'm gonna just give you in a few seconds a break, and then we are gonna just solve this, and that's it. I have written my potential equation for homogeneous permeability, and constant velocity is this guy here. And I am solving it with the direction z, because I want to have a vertical porous sample, and that's my z direction. I know that the integration of this would tell me that potential is a plus bz for z between 0 and the L is where I have my porous sample, where my porosity, permeability are all constant, which means here, which means this part. This porous sample has constant permeability. It is homogeneous. So Z from 0 to L, which is the length of this porous sample, stays constant. K stays constant. So potential is linearly changing across this porous sample. On top of this porous sample, I have put a water column with LW. And I would like to know my potential and pressure distribution. Potential and pressure distribution across this sample. Across this sample. I'd like to know my potential. I want to know what's my potential here, 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 here. What's my pressure at those levels too? And what is my velocity? These are my questions, especially velocity or flux, because I want to know how much water flows through this sample, because that is important for my design. And that's partly what Darcy did actually. He wanted to know the water supply to the city of Lyon in order to do the filtering process and also supply of the water. We wanted to know the flux of it, how much water is passing through this sample. And the sample has a water column on top of it with the constant length of W, LW. For example, 12 centimeter, but it doesn't have to be given any number. I mean, with any number LW, we can solve it. And then later we can fill the numbers there. This is just to give you some sense of what we are, what's the length scale of the system. Especially the diameter of this tube is 6 centimeter. So it's this big, 6 centimeter. I have a tube. First part of it is water. The second part is porous medium. Imagine it's a filter. So water should pass through this porous medium. At the end, it will be purified. And we want to design this filter. And so we want to know what's the potential at all cross sections as a function of Z, what's the pressure at all cross sections, and what's the velocity. Okay, we know it's a vertical tube. We know permeability of our sand column is K1. And we know the pressure at the top and bottom of the sample is atmospheric. And that's why we have this triangular shapes. They are hydraulically showing that it's open to the atmosphere. So water is flowing through this filter and is discharging to the atmosphere. So pressure here, pressure is atmospheric pressure. At this very top, also pressure is atmospheric pressure. And obviously, you can imagine that I have connected this with a pipe, with a pump of water that would supply water to this system and keeps it at constant LW all the time. So since water is flowing through, you wouldn't observe any drop of the level of water. It would stay constant. Okay, Z at the bottom is taken as 0, so that's my reference Z, and I would like to solve this problem, and that would be the end of the lecture, mainly. So it's 11:53. Please take about 15-minute break. Be back here about 3 minutes past 12. So about 12, come back so that until we connect, we can do the rest of the course. So I'm trying to just see how I can. Okay, we stopped here. We would like to solve the potential across the porous sample and the water column. And we would like to know the pressure P, and we would like to know the potential phi. So I assume that everybody sees my screen, by the way. So if you're not seeing my screen, please let me know. So with that, We said that we are going to solve it in z direction, which means z is pointing upward. Start from 0 to L plus LW. That's the total length up in here. The first part is L, which is porous. The second is LW, which is the water column. At the bottom and the top, the system is exposed to atmospheric pressure. And that's the triangular shape that is being shown in the top and in the bottom. Okay, now let's go ahead and find the potential distribution across the sample and pressure distribution and velocity. Okay, so stay very focused with me so that we can do things step by step properly. Now, the first thing I would like to know is this. What is the potential at the bottom of the sample? And what's the potential at the top? And what's the potential in the cross section between water column and the porous sample? Okay, so what is the potential here at the bottom of the sample? Potential at the bottom where the pressure is set to be the atmospheric pressure is what? Potential is P plus rho GZ. What's the amount of Z?
0. So it
Zero.
will be P.
So at the bottom, Z is 0. So then it will be P at the bottom. And the pressure is atmospheric pressure. So let's assume everything relative. So let's assume atmospheric pressure can be deleted from the entire system. So we just do relative pressure. In that case, I can just say that the pressure at the bottom is 0 and pressure at the top is also 0, but the relative pressure, not absolute pressure, relative pressure. And that means that I can now solve everything relative. So I have pressure at the top is also 0, and I would like to know the potential at the very top. Potential at the top is P plus rho GZ. What's the Z of the very top?
L plus LW.
Exactly, it's L plus LW, which is the length or the end of the entire sample. Porous plus the water column. Pressure is set to be 0 relative pressure. So I'm going to get rid of this pressure here too. And I would like to assume that now with this, I can write potential at the top is rho G L plus LW. Potential at the bottom to be 0. Again, I am assuming that pressure atmospheric is 0, which means relative to the atmospheric pressure. If I wanted to write it absolute, not relative, then there would be pressure atmospheric, P atmospheric, which is 10 to the power 5 Pascal, would be added to all of these values. I am deleting this 10 to the power 5 from everywhere, from the bottom and the top, both. If you wanted to work with absolute pressure, you would write this atmospheric pressure as well. In short, we write it most of the time PATM, which is atmospheric pressure. It's not the cash machine, it's ATM. This is atmospheric. Okay? So that would be in absolute form, it would be 10 to the power 5, but in relative, I'm just going to assume that this is 0, and this is rho G L plus LW. How about the potential here? How about the potential here? I would like to have an interactive discussion with you to find the potential in between, because that's not the most trivial thing to come up with. But the more you interact, the better and the more clear this would be. How would you think that the potential can be found? The first thing you need to do all the time is to replace potential with P plus rho GZ. This would give you the potential at any point. Do I know the pressure there? Do I know the Z there, yes, I know Z. Pressure, a little bit tricky here. But let's work on this. What derives change of potential? What law gives us the change or gradient of potential and related to velocity? Darcy's law, right? Darcy's law says U is minus K over viscosity, potential drop, gradient of potential. Potential will drop because you have permeability. Because rock isn't the perfect channel for you to flow, you will have a kind of a convenient factor, how easy the flow can happen, K, inverse of its resistivity or its resistance towards flow. And then you have gradient of potential. What happens if you have a fixed velocity, a natural velocity, you're going to have some velocity, physical velocity in this sample, right? If velocity is fixed, what would you do if K goes strong, if K becomes high and high and high? What would happen to the potential gradient if the product should stay the same?
It will decrease.
It should decrease. When A times B is constant, if A becomes bigger, 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 B should be smaller, 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 so that the product is constant. Now, here, flow is happening through the microchannels of this porous material with diameters of maybe 100 micrometers, 200 micrometers. Here, water is flowing in the big channel of 6 centimeters. What's the estimation of permeability of this big channel based on bundle of tube theory? It's R squared divided by 8, right? From the previous lecture. The potential drop in the water column is extremely small because water can flow very, very conveniently in this big tank or tube. Let's call it tube because it's not tank, it's 6 centimeters. When you would observe potential drop is due to the permeability and the porous structure with microchannels of some 100 micrometers. So in the water column here, between L plus LW to L, between these, potential would not really drop much, very, very little, compared to the potential drop that you would observe here. So between this section to this section, we would assume the potential would stay constant because permeability is so high because there is no porous structure there. It can be just a 6 centimeter diameter tube with no sandpack, nothing in it. It can just flow easily. And then when it starts to enter the porous part of the filter, then it starts to observe resistance. So phi between L up to L plus LW is constant. Because in between, it's only water channel. There is no porous structure. There is no permeability, or there is no resistance for the flow to happen. Of course, if you want to be very accurate, you need to just estimate that K of the tube is R squared over 8, which would be 3 centimeters. So 0.03 meters to the power 2 over 8, which would be 9 10 to power minus 4 divided by 8. It is almost, of course, 9 divided by 8 is not 1, but almost around 10 minus, in the order of 10 minus 4. What's the permeability of a porous medium typically? We are speaking about millidarcy, maximum 1 Darcy. What's 1 Darcy permeability in a square meter?
Power minus 12.
12, exactly. R minus, which is 10 to the power minus 12, and tube is 10 minus 4. So it's 1 billion times more conductive than porous material. So we can just simply, as engineers, we can just simply ignore it. Because the other one, K of the porous sample, is in the order of 10 minus 12, and maybe even smaller. So inside the water channel, we will assume that the potential drop would be negligible. Yeah, so that would be what you would do. Inside here, potential drop would be negligible. And this is exactly what I have written neatly in here. Pressure atmospheric is neglected and it's all relative. So potential at the bottom is 0, at the top is rho g plus times L plus LW. And then finally, what I get is that the potential between, it will be potential between L to L plus LW would be the same potential as the top. This is potential top, which is rho g L plus LW. Assuming that water column is not porous, that's not an assumption, this is a fact. So its permeability is 10 to the power 8 times more than the permeability on porous medium, if the porous medium is 1 Darcy even. If not, if it's a smaller, that would be even much bigger than 10 to the power 8 factor. So we assume that the potential in the water column does not change. It doesn't drop because the potential drop is very small, extremely small. Now, what about between this? Between Z is 0 to Z is L, we have porous medium. Potential now in the center point here, in the section between porous and water column, is rho g times L plus LW. Now between this value to 0, you are gonna have potential drop. So how would this look like at the end of the day? How would this look like at the end of the day? You have a porous sample. I am just plotting it here, and I would like to go through Z, which is elevation. And then in the horizontal part, I have potential. I know that the potential at the top, which is here, potential is this much, which is, this potential is rho G L plus LW. So that's the potential at the top. I know the potential in the section between water column and porous medium is also the same value. The same value. So potential would not change between my water column section. It would stay the same value as shown here. So potential would be rho G L plus LW. Now, at the bottom, what's the potential at the bottom? 0. Which means at the bottom, potential should be 0. So between the midsection to this end section, potential would linearly drop, would decrease, 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 decrease all the way to 0. That would be the potential. This is potential at the beginning is constant in the water column, and then it drops linearly to 0. Almost constant in the water column with permeability of 10 to the power minus 4, around minus 4. So what's the line formula here? What's the line? This line. We know that it is
permeability.
This is A plus BZ, right? It's a linear function. A line which goes from 0 to rho G L plus LW at Z equals L. This is L. So I know this is a line. So that's a line. The line at Z equals 0 is 0. The value of this line at Z equals L is rho G L plus LW. So what would be the mathematical function for this line? When at Z equals 0, potential is 0, what can we say about A? We know that the line formulation is A plus BZ. When you put z equals 0, put z equals 0.
A is the potential.
So b times z should be 0, then a will be 0. So this means a is 0. We need to find a and b in order to find the line formula. If z is 0, potential needs to be 0, it means a is 0. If z is L, my mathematical function says a is now 0, b times L, because z should be set to L, is equal rho g L plus LW. That means b is rho g L plus LW divided by L. So with these, I can say my potential is a linear function that is actually is rho g L plus LW over L times Z. That's the mathematical function of this line that I plotted here. A is 0, B is rho g L plus LW divided by L. And that's exactly B. This is B. So that's the mathematical function of the same line that I have just plotted here. It's a line that passes from 0, 0 and rho g L plus LW potential at the L to be Z. This is the line. So this is the mathematical function for the potential between Z of any number between 0 to L for this zone, where Z is between 0 to L. From L to L plus LW, Z stays constant with its maximum value of rho g L plus LW. How about pressure? How can I now plot pressure? Now, this is the potential distribution, and neatly presented here is this, and that's exactly the function that I wrote in the other slide here. So that's the potential. How can I find pressure? What's the relationship between potential phi and pressure P? Potential is pressure plus rho g Z. So let's find what's the pressure across this sample and plot the pressure in the left plot. What's the pressure at the top? At the top. What's the value of the pressure? It was atmospheric pressure that we assume, absolutely. It was atmospheric pressure that we assume it's 0 for now because we deleted atmospheric pressure from both top part and bottom part. So we are going to just make it 0. But we know that 10 to the power 5 is just subtracted from the entire system. So at the top, it's atmospheric that we just say it's relative to atmosphere is 0. Relative to atmospheric pressure becomes 0. And it is also seen here too, when potential is rho gz plus P, and we know that P is P atmospheric, so we can just say it is 0. What's the pressure at the bottom of the sample? At the bottom, again,
Also 0.
Atmospheric, so it is 0. What's the pressure at this cross section between Porous and the water channel?
The water column.
What's the pressure here? Let's find it. What's the potential here? Potential
rho GL.
Yeah, it's rho g. That's a great thing that you said. It's just rho g L plus LW is the potential. If potential is rho g L plus LW, if potential is rho g L plus LW, what would be the pressure? We know that this is pressure plus rho g Z. What's the Z at this elevation? L. So we put L here. So rho g L is here. What should be the pressure? Rho g L W. So that the summation of them becomes rho g L plus LW. So pressure at Z equal L is rho G L W. That's the pressure. And it's true because it's like hydrostatic pressure. You go LW inside the water. So that's the static pressure you feel. So pressure between top to the cross section becomes this. And then between the cross section to the end of the sample, pressure becomes that. This is not the most straightforward plot that you would assume. Pressure at the beginning increases in the mid of the sample, then decreases, again goes back to 0. This is the pressure distribution. The middle part is the potential distribution, and the two are correlated, and the correlation is potential. The right one is pressure plus rho Gz. Now, if you add the pressure plot with rho Gz, you will get exactly the potential curve. You will get the potential curve. So in that case, you can simply add, I can't unfortunately change the color here, I think, but if you say rho Gz, if you have rho Gz, imagine this is the new line that I'm plotting is rho Gz. It should also go through rho Gl. At this point, it should be rho Gl, so it can be generally any number. So imagine this is, because rho Gz just increases with the slope of rho G, and then Z0 becomes 0, then Z1, Z2, Z3, it just goes like this linearly. If you add the two curves together, the dashed one and this horizontal or rotated V curve, V-shaped curve, then you're gonna get exactly the potential curve, which is here, this one and this one. In fact, if I want to just describe it a bit more qualitative, pressure is increasing this way, and then you have the curve of the potential, rho Gz part. The summation of the two would give you constant plot, that the potential would not change across this sample. And then here you would have linear change of the potential, and the other part it would have also pressure to look like this V shape. Now I'd like to just describe a little, discuss a little bit about the concept of pressure and the concept of potential. See, what is the pressure? What is the potential? Potential is the part of the energy, perhaps better to say, that derives flow. Potential gradient is Darcy's law. U is minus K over viscosity gradient of potential. Potential difference drives the flow. Okay. Pressure is thermodynamic part of it. P is the pressure that goes to PV is nRT, is ZRT that you have seen in gas law. This is the pressure that when it goes to atmospheric pressure in the water would boil at, let's say, 100 degrees. The pressure that we say is that pressure, atmospheric pressure, and all the kind of feeling of the pressure, the thermodynamic part of the pressure is P. P is the part of the pressure that would go to the equation of a state to decide, are you having water in liquid phase or vapor phase? What's the density? Density is dependent on pressure, right? Density is not dependent on potential. It depends on pressure. And that's exactly this term. So pressure is the thermodynamic part of the entire potential that would be important to drive the flow. If pressures are the same, however, you would have different potential because of rho Gz is different, you still would see flow. You still would see flow even though pressures are equal. Okay, so there is a major part, which is Darcy's law, is proportional to gradient of potential. And then potential is thermodynamic part, which is pressure. Then it is hydrostatic part, which is rho gz. It, in fact, I guess it was, you know, you asked me in the first lecture that, in fact, actually, there is another part in the potential that we have neglected, and that's the kinetic part. That's the kinetic part of the energy, or the driving force for flow. We have thermodynamic part, hydrostatic part, and then we can have the kinetic part, which we have ignored. Only Forchheimer part will bring it if we have non-Darcy flow. Okay. So for now, what we can say is that with this given Sandpack, we can obtain the potential distribution and pressure distribution. And now your project one is very much needing this science, this knowledge, in order to be addressed. Okay. Now I would like to just finish the course with a few minutes of going a bit forward. So that's exactly the same plot, now neatly plotted. So I have it in here, so it's being recorded and you can watch it later to see exactly the nice plots here. That's the potential, and this is the pressure, assuming that pressure atmospheric 10 to the power 5 is taken out. If you want to do that, you can add it back, then everything would be shifted by a constant 10 to the power 5, also to the right side. The beauty of mathematical description is that we don't have to only stay in this system, which is vertical or horizontal, I mean, X and Y. We can study radial flow with the same concept. We can study flow around wells, which are more radial rather than linear, like this, X and Y. So in that case, you need to know divergence operator. You need to know divergence operator in radial coordinate or in spherical coordinate or cylindrical coordinate if you are in 3D. In 3D, if you write your Darcy's law in cylindrical coordinates, which means you have a well, and then you want to know the flow around it. So that would be the radial in 2D or cylindrical in 3D flow. The operator divergence has derivative with respect to R. It has derivative with respect to the angle theta. Theta is this angle. And it would have derivative with respect to Z, which is the depth. In one dimension, it can be seen like a radial flow, which is derivative with respect to R only of the velocity times R. And I would replace velocity R with Darcy's law. Darcy's law says R d phi dr with negative sign is my, K over mu times d phi dr with negative sign is my Darcy's law, which is written here. U is gradient of potential times minus K over viscosity. Gradient operator would be ddr, 1 over r dd theta and ddz. For 1D, I am going to use only this part of it, and I'm putting it here. That's the gradient operator with minus K over mu, of course. And then if permeability and viscosity are constant, I'll get this formula. For vertical direction, for Z and X, I got d square over dz of phi. So for Z direction, for Cartesian coordination for in Z, I got second derivative of potential with respect to Z was 0. For radial coordinate, which is like this, and I only have radial dependency of the pressure with R, nothing would change across theta or Z, I'll get more complicated equation. It is having an R inside still. So I can't just write it d square phi over dr2. It has ddr of r times phi. Now, if you solve this problem, this is a flow around wells, which can be seen for a steady state flow yet, still a steady state, and it is in 1D radial only. If you solve this equation, you will get that function. So you have that equation. And if you are assuming that that is your well bore with radius RW, and then you go like this is your R coordinate, and you have horizontal flow. So horizontal flow means potential is pressure plus a constant. So gradient potential and gradient pressure are equal because there is no change in Z. Change in Z is 0. Then we can replace it with the pressure equation because ddr of potential will be equal to ddr of pressure. And we know the total flow rate of my well is velocity times cross-section area A. If I do so, I find my cross-section area velocity times A, which is the flux of my well, is 2 pi RH, which is this cylindrical cross-section. At any point, I can do that. At any point, I can do that. Minus K over viscosity dP dr. If I do all the mathematics, which is extremely convenient here, it's just integration. For that, the only thing which is required to be known is that dr over r integration is logarithmic, is ln function. You will get a formula here when you do the integration from the well radius, from the well bore radius to the some radius far from the well, you will get the flow rate as a function of pressure drop, H, permeability, and logarithmic ratio of a logarithm of the ratio of RE with respect to RW. RE is some radius far from well. It can be any R. You just call it R, then it would be R. And that's exactly the well equation that we have, and the Peaceman studied that many years ago to obtain well formulation. So I hope that this if you plot that function, you would get that this well function, the pressure distribution across the well, is logarithmically changing across the space X, and that's the pressure of the well. And you can see that the most drop of the pressure around the well happens near the well bore because of this logarithmic function. And far from that, you are going to have a slower decay of the pressure. Okay, because the flow rate that you have in your well is proportional logarithmically to the radius r that you are going to look and study, and obviously dependent on the well bore radius as well. Okay, so delta P, which is pressure at the well with any other location like E or any other location, P, would be proportional to the flow rate that you have in your well, permeability, cross-section area, viscosity, and the logarithm of the ratio of the R you want to study the pressure at and the R of well. Okay, now this was quite brief and very much getting you exposed to this. We used to have in previous years about 3 lectures on this subject, so 3 times of 1.5 hours to go through steady state well flow, semi-steady state, which is pseudo-steady state, and transient, which would then form the basis of well testing science. We are not going to have them any further any longer. If I get time, I'm going to record those offline for those who are interested in well testing science to learn about it. What I wanted to say here is that flow around the well can be also modeled with Darcy's law and a steady state incompressible flow which is divergence U is 0, and Darcy's law. We just sum the two up. For 1D case, we get a formula that would drive our flow around the well. And that's the steady state well flow rate that Peaceman studied many, many years ago, and he found the well productivity index based on exactly Darcy's law around the well at a steady state and the continuity equation, which is divergence of U. What I like you know from this whole story that I said is that the thing that you did in simulation course to relate your source term of well to be a function of your delta P is actually coming from Darcy's law and incompressible flow science. And that also shows that most of the drop will happen just near the well bore. Just to close the lecture, the close to the well effect, what do you observe is that pressure distribution mostly happens near the well. With this continuity and Darcy's law, and some mathematics that we need to know all the integration, and that's all, we find the pressure drop as a function of Q, viscosity, permeability, and logarithm of the radius that we are trying to find the pressure drop at. Mostly the pressure drop happens close to the well. And permeability near the well is extremely important for geoscientists. That's where the connection between well and the reservoir takes place. And many times when we drill well and we are producing or injecting dynamically or statically, we are gonna lose productivity. And that productivity loss is called the skin. We are gonna have clogging of our well. We are gonna have debris for the production debris, or when we drill well also, there are a lot of technological advancements that have taken place in order to enhance the productivity. Remember one thing, all we can do with the reservoir is through the wells. We can change the pore pressure, we can increase pressure, decrease pressure, conduct this, make, I don't know, geothermal, storage of anything. It's all through wells. Near wellbore physics is extremely important to keep productivity or injectivity right. And a lot of these sciences can be just found with as simple a study as Darcy's law with mass conservation. Darcy's law with mass conservation would give you already the pressure dependency with respect to radius location and productivity rate Q and so on. If you have higher productivity rate, you would have delta P higher. If you have permeability very high, since permeability is in the denominator, if permeability is very high near the well, you need smaller delta P to keep the same flow rate. That's the whole science here. If K is high, since K is the denominator, when K is extremely high, you need smaller pressure drop to cause the same flow rate Q. That's why permeability near the well is extremely important. And especially if K is a small, then we are in trouble. You need a lot of pressure drop in order to maintain productivity. So the last words, there are many areas, many reasons for a skin to happen. The productivity at the well be complicated. Debris, drilling debris. There are so many other type of Forchheimer parts as well. Kinetics also causes drop of the pressure potential. And there are many schemes, many technologies that allow us to enhance the productivity, enhance the injectivity through reactive transport processes, through so many other advanced technologies, not as the scope of this course. All at the end, remember one thing. From the nature, the question we started lecture today also, from the nature to mathematics is about conservation laws with boundary conditions, equation of a state, and so on. From there, you describe either you are in horizontal, vertical direction, then you do Cartesian system. Then you can solve these sort of problems. You are in radial systems, you solve them radially, and so you will get the well productivity. The well part is really something like a flavor for this course, not really the the scope of it or any focus of it. I just wanted to show you an illustration of what can you do with that, the same concept here. Here, this is extremely important, and you have a project for it, and I hope it was clear for you. So thanks a lot. I'm going to stop sharing and recording, and then I will get any